So welcome. We are going to discuss about prime numbers and few facts about them. So first of all, what is a prime number? So prime number is an integer which is greater than 1 that is not divisible by any positive integer except 1 and itself. So note that there are, what is the qualification? That it's greater than 1 and it should not be divisible by any other number except for 1 and itself. Okay. So this is what is the definition of prime. So let me give you a few examples. The examples could be 2, 3, 5, 7, 11, 103, etc. So on. So these are the prime numbers. Now, second, so all integers which are greater than 1, which are not prime, are called composite numbers. So, definition. An integer greater than 1 that is not prime is called composite or composite number. Composite for short. Okay. Now, examples would the examples would be say 6, right? So 6 is divisible by 2 and 3, right? So there are numbers which are bigger than 1, but other than 6, which divide 6, 2 and 3, for example. Similarly, you can have 18, which is what? 2 times 3 times 3, right? So there are these numbers which divide 18, which is neither 1 nor 18 itself. So these numbers are composite. So then the question is the following. How many primes are there? So for that, we have the following result. There are infinitely many primes. Okay. Before we prove this result, so this is a theorem, there are infinitely many primes. So before we prove this result, we'll prove a lemma. So lemma. Every integer greater than 1 has a prime divisor. If you take an integer greater than 1, it will have a prime divisor, right? You may ask, what if it itself is a prime? Then it divides itself, right? So it has a prime divisor. So let's prove this. So proof, and we'll proceed the proof by contradiction. So proof by contradiction. Let me write down proof by contradiction. So what we'll do is the following. We'll try to assume that there is a integer greater than 1 which has no prime divisors and come to a contradiction to some known fact. Okay. So assume there is a positive integer greater than 1 having no prime divisors. So it has no prime divisors. So now consider the set S of all n such that m is greater than equal to 1 is an integer and m has no prime divisor. Clearly, from the part 1, you can see from 1, it follows that S is non-empty, right? Because the first, we already have there exists a positive integer n greater than 1, which has no prime divisors, right? So S is non-empty. So therefore, and also S is a subset of n by the definition, right? Because it's a integer greater than equal to 1, so it's a subset of n. Therefore, the well-ordering principle kicks in. So by well-ordering principle, S has a least element, say n. Now let's investigate this n. So n belongs to, since your n belongs to S, S has no prime divisors, right? N has no prime divisors on S. All right, so now, so clearly there is no prime divisor for n. So the only number which divides basically n, so this means what? This means n has no prime divisors. However, n divides n. This would mean what? But n divides n, right? Every number divides itself, but n divides n. This implies n, which is the divisor of n, is not prime, is composite. This means what? There exist A and B belonging to n, that A is less than n and B is less than n with what? With n equals to AB. So now, if since we have, because A is less than n, this would imply that A is not in this list S, right? A does not belongs to S, right? Because M was the, n is the least element. Yeah. So therefore, what should happen? Therefore, A must have a prime divisor. Okay, because we collected all of them in this set here. Whatever integer does not has a prime divisor was collected in S. However, since A is not in S, we can say that A must have a prime divisor, which will also be prime divisor for n. Now, why is that? Recall, we had the following. If A divides B and B divides C, this implies A divides C, right? So this means what? A divides n, sorry, we have A a prime divisor, A has a prime divisor, let's call that P. P divides A and P divides, P divides A and A divides N, therefore that prime divisor divides N, which is a contradiction, right? So this is a contradiction. This is a contradiction. What is it contradiction to? Contradiction to the fact that N has no prime divisors. Therefore, our assumption must be wrong. Therefore, our assumption is wrong. Our assumption is wrong. Therefore, what? Therefore, every positive integer greater than 1 must have a prime divisor. Must have, or at least one prime divisor. Okay. So this is the proof for this lemma, which says that every positive integer greater than or equal to 1 has no prime divisor. Okay. So let me call this lemma 1. Okay. Now we can go back to the proof of our theorem of being that there are infinitely many primes. Let me rewrite the theorem again. Theorem. There are infinitely many primes. Again, we'll prove this by contradiction. So proof by contradiction is really very powerful. So proof again by contradiction. Now there are many proof of this theorem. Okay, this proof is basically given by Euclid, and Euclid wrote this in his Elements book, Elements. So let's see the proof. All right. So again, proof by contradiction. So suppose there are finitely many primes. So let's label them. Say P1, P2, all the way until Pn. Yeah, for some positive integer. Now consider this following number q, which is take P1, P2, multiply them all the way until n, and then plus 1. Now let's try to see. So this number q is an integer greater than 1, right? Therefore, by lemma 1, which you saw here, this lemma, which says every integer greater than 1 has a prime divisor. So this, by lemma 1, q has a prime divisor. Let's give it a name, say P. Yeah, so it has a prime divisor P. Now note that P is not Q. Sorry, P is not Pi for any I. Why? So Why? For if not, you will have P, if P equals to Pi for some I, you have P divides Q, and of course, P being multiplied in one of these guys, P will divide this one too. So therefore, P will divide Q minus P1, P2, Pn. This implies P divides what? This is going to be Q minus this part, which is going to be 1, which is contradiction, which is not possible. Right? Because it's a prime, it cannot divide 1. Yeah. Therefore, what? Q must be a prime not listed in P1, P2, Pn set. This implies what? This implies, right? Because in that case, that means the Q has no divisor other than 1 and itself. So Q must be a prime, which we have not listed. So therefore, what do we get? So sorry, P, my bad. P must be the prime, which, because P. So P must be a prime not listed in this set. Therefore, what do we get? Therefore, this contradicts our assumption that this is a complete set of primes, right? So this contradicts that our set was complete list of primes. That means there's no complete list of such primes, right? This implies there are infinitely many primes. Okay. So then the question is, so we know that there are infinitely many primes. So then the question is how to find the primes. So one may say, well, randomly pick an integer. And the question is, if I randomly pick an integer, what is the chances of it being prime? Okay, so these are two different questions. So before we do that, let's see, if I give you a prime, how to basically decide whether it's prime or not. Okay, so we'll do what is called as Primal T Test. So what is a Primal T Test? Primal T Test is a test given an integer n, and of course our definition of prime needs us that n is greater than 1. Is it a prime? So now there are many algorithms in this regard. If you are slightly interested in complexity theory, there are primes. So there was a paper written called Primes in P. So Primes in P by Agarwal, Kayal, and Saxena. Yeah, they were in the same institute as I was. He was a computer scientist, and these two were his undergrad students at that point of time. Okay, anyway, so this is the best known. So primes in P means finding whether a number is prime or not is a polynomial. It can be done in a polynomial time algorithm. And then after that, there has been a variation of this algorithm, or there's a polishing of this algorithm further, right? If you're interested, please look at this paper or let me know. I'll post the link on Canvas. Okay, but let's start with basics. So here, so we need a method of determining whether a number is prime or not. So so if I give you so for that we have the following: if n is a composite integer and you want to find the prime factors of it, how far do you need to go? Well, one way is to check all the way from 2 to n minus 1, right? But that's not the optimal. It's far from being optimal. But there is another suboptimal way of doing it, which is the following: if n is a composite integer, then n has a prime factor not exceeding square root of n. Okay. So let's see the proof. The proof of this. Now, since n is composite, this implies there exist a and b such that 1 is less than a, and we don't know about this. These two could be equal. So a less than equal to b less than n, such that n equals to ab. Okay. Composite means there are two factors uh, which are basically at least two factors which are bigger than 1 and less than n. Now, claim that a must be less than square root of n, less than equal to square root of n, right? For if not, so a must be less than square root of n. If not, what will happen? If not, then a will be greater than square root of n. B is already greater than equal to a, which implies b is greater than square root of n. This implies ab is greater than square root of n times square root of n, which is going to be, so ab is greater than n, which is a contradiction. Which is a contradiction, right? Because contradiction, what does it contradicts? That ab equals to n, right? So therefore we get a is less than equal to square root of n, which proves our. So based on this theorem, what we need to do is to check if n is prime or composite, divide n by all integers, or actually prime all integers less than or equal to square root of n. Yeah, so the procedure is divide n by all the integers less than equal to n. Of course, all the integers positive. So let's divide by all integers k such that 1 is less than, so 1 is greater than k. I'll rewrite this: 1 is less than k, less than equal to square root of n. If no such k divides, if no such n, then n is, sorry, if no such n divides, if no such k divides n, then n is prime. So this method was applied, this procedure is called, so this algorithm or procedure, this procedure is called sieve of Eratosthenes. Eratosthenes. So he was an ancient Greek mathematician. He was Greek. If I remember correctly, he was around Alexandria area, right? So now let's see how can we employ this to check whether a number is prime or not. Okay, so or to find factor of it. So let's take is 1041 is 1041 the question is 1041 a prime. Okay, so we want to basically answer this question. So whether 1041 is a prime or not. So what we need to do is basically, so we'll use the sieve. So you will use the sieve of Eratosthenes. Okay, so of Eratosthenes. So square root of 141 is roughly around 32, 33. So this is going to be less than equal to 33. So it's around 33. It's actually 32 point something. So you need to go all the way until what? 33, actually to 32, because there's a 32.4 something, 32.2 something, 26. So you need to go until 32.26 to check it out. So let's see. So let's check. So what are the primes which are less than? So 2, no. 3, does it go? So 1 plus 2, 1 plus 4 plus, we got already what? 6. Oh, wow, 3 goes in it. So 3 is the, so we already can see 1041 divided by 3. So 3 ones are, so 3 3s are 9, 1 4, 3 4s are 12, 2 1, and then we get 347. So basically 1041 is 3 times 347. So you got factorization of 104. You got one factor of this. Now you can keep repeating this process actually. So how do we go about it? You can, so suppose you want to ask, can I complete factorize? Complete factorization of 1041. In that case, we already got 1041 equals to 3 times 347. And now what we need to do is we need to factorize 347. Yeah. So although this is a check only to find whether a number is prime or not, you can extend this sieve of Eratosthenes to find out the factors, all the factors as well. Although this is tedious, there are better ways to do this, but 3 times. Now let's see. So square root of 347 is roughly equal to 18.6 something. So we need to go and check until what? Until 17, because 18 is not prime. So until 18, let's say 18. So let's check. Is it divisible by 2? No. Is it divisible by 3? So we are looking for factorization of this guy. Is it divisible by 3? You have 8 plus 7 is 15, right? So 3 plus 4, 4, sorry, yeah, 7 plus 7, sorry, 7 plus 7, 14. No, it's not divisible by, it is not divisible by 3. Next one is 5. No, not divisible by 5. So let me write down 2, 3, nope, 2, no 3, no 5. What about 7? So if you divide by 7, you can see divided by 7. So 7, what? So 347. So 7, 7 4s are 30, 7 5s are 35. So 7 4s are 32. You get what? 27. So no, 7 is also not there. Then what about 11? So if you look at 11, 11, let's see 11. So 11 goes how many times? So 11. So 11 is basically 11 threes are 33. 1, nope, 11 doesn't. What about 13? So let's look at 13. 3, 4, 7. 13 ones are, sorry, 13 twos are 26. We get what? We get 8 and we get 7. So so 3 nines are 27. So this will not go. So 3 fives are 64. Sorry, 3 fives are 13 fives are 65, but 13 6 is, so it doesn't goes in there. So not, nope, not 13 either. 13 doesn't goes in it. Similarly, you can check what is the next one. So 13, nope. Then the next one is 17. Nope. So this means what? This is a prime, right? So this is a prime. So you get 1041 is this guy. So this is what is called C of eratosthenes. All right. Okay. So that take cares of this thing. So we'll later on see that there are better primal T testing. But let's ask the following question. Uh, how many primes are there roughly less than equal to X? Yeah, that's a meaningful question to ask. So if I give you a number, so suppose I ask you, so let's define the following definition. So the definition goes the following way. If you look at, let pi of X be all the primes. So P be a prime such that P is less than equal to X. And if you count the size of this set, yeah, so this denotes the size. So question is how many, so this counts how many primes are there which are less than equal to X. Yeah. So this phi function. So if we can find an estimation for phi function, we'll get the idea of it. There are no fixed results about it, but we have what is called an asymptotic result. What is an asymptotic result? Asymptotic result means in long range, pi x behaves as like x log x, where log x is basically log of x base e. Yeah, it's not, I mean, some people use this as ln x, but most of the number theory books use log x for instead of ln x, so we'll use the same result. So what does this really means? This means that if you take limit as x goes to infinity, pi x divided by x log x, if you look at this limit, this is 1. This is what it means asymptotically. I mean, another example is look at n square and n square plus 4n plus 1, right? So it means that asymptotically these guys are same, right? That means they are of same size really. Why is that? Because if you look at n square plus 4n plus 1 divided by n square, limit as n goes to infinity, this is basically 1. So same thing here as well. If for x sufficiently large, pi x, which is number of primes, less than equal to x, and x over log x will behave the same way. That means the size is going to be more or less the same. So then, so this is a question about, so there are a few more results about primes. So another one is called primes in progression. In arithmetic progression. So progression, this is also called Ditchley's theorem. So let's just basically use that. So Ditchley theorem on primes in progression. Let's just borrow the space here. So what does the theorem tells? So suppose A and B are relatively prime. That means that GCD is 1. So A and B are relatively prime. A, B1, where A and B are positive integers. Then the arithmetic progression look at an plus b, where n belongs to n. If you look at this arithmetic progression, or if you look at this set, right? If you look at this set, contains infinitely many prime. There are no elementary results on this, but yeah, hopefully later you should be able to see the proof, not in this course. All right, so now, so this is the Ditchley's theorem. Now, I think we should stop at this for today. Thank you for your attention.